All right, so we move on through the chapter. We're almost done, just a couple more sections. We go over 11.5, which is power series and Taylor series. So Taylor, the name Taylor, you may have learned before when we cover 11.1. We're going to go back to Taylor. However, we're not just going to do polynomials. We are going to convert those into infinite series. You'll see later when we move on to the section. What are power series? But first of all, let's see what we have done so far. Okay, so we have done working with series with constant terms and determine whether do they converge or diverge by looking at different tests such as the p-series, the geometric series, the telescoping series, what else, the comparison test, the integral test. Okay, now what are we going to do? We're going to work with series with variable terms. With variable terms, that is series with x in the general term, as you will see soon. Okay, so this section will rely with some of the techniques that we have learned that you may have learned back in the intermediate algebra course, such as working with factorials, okay, and pattern recognition. We have done a little bit of pattern recognition when we cover infinite sequences, when we were given the list of the sequence and come up with the general term by looking at the pattern. But we're going to revisit that. And the first thing we're going to do before getting into power series is work with factorials. Okay, what are factorials? A factorial of a number n is denoted and the exclamation sign, which by the way, it's not an excited number. I know it looks like an excitement symbol, but no, it's not. Okay, and it's equal to the product of all the positive integers less than or equal to n, for example. In a more generalized way, we are going to have n factorial, which equals n times n minus 1 times n minus 2 times n minus 3 dot 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 dot, dot times 3 times 2 times 1. So we multiply all the numbers below n and n itself. Okay, so here I have a short list of the factorials. It's a very tiny one, of course. We're not gonna. There is a key on the calculator to generate these factorials. The ones that we need to keep in mind is that 0 and 1 factorial are always 1. Okay, 2 factorial, that is multiply 2 times 1, which is 2. 3 factorial, 3 times 2 times 1, which is 6. 4 factorial, multiply 4 times 3 times 2 times 1. See how we multiply all the integers below n times n itself, and then 5 factorial, 5 times 4 times 3 times 1, etc. And so on and so forth. Okay, and see how these get big every time, like really quickly, very quickly. I mean, 5 from 4 factorial, which is 24, we go to 5 factorial, like really big in a 1 to 120, and then a huge jump to 720, and even bigger to 540, and even way bigger to 40,320, right? All right, let's simplify expressions involving factorials because we are going to need this to find some limits involving factorials. All right, so this is what you don't want to do. You don't want to evaluate 9 factorial to get a big number and 7 factorial to get another huge number. So the technique here is to identify the factorial with the largest number. So in this case, the factorial with the largest number, I'm going to highlight it with green. It's going to be the 9 factorial. That is larger than 7 factorial. How are we going to simplify this? Okay, so I'm going to use the definition of the factorial. So keep in mind that 9 factorial is the same as saying 9 times 8 times 7 times 6 times 5 times 4 times 2, 3 times 2 times 1. 9, 8, 7, 6, 5. Yes, have it correct. Okay, however, I'm not going to write all this down here. I'm going to do the following. 9 times 8 times 7, And I'm going to stop at the number that it's the same as the one that I want to simplify. Keep in mind that this, which I'm highlighting, 7, 6, 5, 4, 3, 2, 1 is the same as saying 7 factorial. So really 9 factorial is the same as 9 times 8 times 7 factorial. So I'm going to write down the 7 factorial over here. And what am I going to do? I'm going to cancel this out. So this will be 9 times 8, which equals 72. Without even actually evaluating the factorials to deal with huge numbers. All right, what are we going to do with the next example? So we are going to identify the largest of them. In this case, the 12 factorial. Okay. And in this case, I'm going to cancel out to divide out the 10 factorial in the denominator by expanding a few factors of 12 factorial. 12 times 11 times 10, and I'm going to stop there. I'm going to put a factorial, divide by 3 factorial, which, by the way, this is a small one. I'm going to write down as 6 times 10 factorial, which I'm not going to simplify. I'm just going to keep it like this because I'm going to divide out these two. Okay, so this 6 divided by 12 divided by 6 is going to give me a 2 times 11, which equals 22. And that's all we do, rather than expanding this huge number, and well, this is a tiny number, so no big deal. All right, let's look at letter C. Now that factorial that contain variables only, no numbers. We still do the same, identify the factorial with the largest number and write it in terms of the factorial with the smaller terms. So for example, n plus 1, we would write, okay, let me do this on the side, n plus 1 factorial. This would be the same as n plus 1 times n minus 1 times n minus 2, etc. However, I'm not going to write everything. I'm going to take advantage of this, which is n factorial, to rewrite n plus 1 factorial as n plus 1 times n factorial. The reason why I stop there is because I have another n factorial in the denominator. Boom, boom. Cancel out. N plus 1. Final answer. All right. What about this one? Okay, letter D. Let's identify the factorial with the largest value. That is n factorial, because that is larger than n minus 1 factorial. So that's the one I'm going to expand. So that'll be n times n minus 1. And I'm not going to go n minus 2, n minus 3. I'm going to stop here at n minus 1 to cancel it out with the 1 in the numerator. Okay, divide this out, I get 1 over n. Keep in mind the n here is in the denominator. Okay, another one. N plus 2 factorial divided by n factorial, n plus 2, n minus n plus 1, and n factorial. I'm going to stop there because I have another n factorial in the denominator. Goodbye. They cancel out. N plus 2, n plus 1. Okay. Final answer. Letter F, identify the largest factorial. Correct. The one in the denominator. N plus 3 is larger than n plus 1 indeed. Okay, so let's take a couple steps to simplify this one. So n plus 1 factorial, leave it like this. The denominator, expand a few factors. N plus 3 times n plus 2. Subtract 1 every time you develop a new factor. And then n plus 1. I'm not going to write n minus 1, n minus 2, and so on, because this is exactly coincident with the one we have in the numerator. Okay, and no more factorials involved. So we are going to be left with n plus 3 times n plus 2, everything under 1. All right, what about letter D? For letter D, n factorial squared. I'm going to write n factorial squared as n factorial times itself, n factorial, divided by n minus 1 factorial times n plus 1 factorial. Okay, now I need you to observe something. Notice n factorial and n factorial, they are of the same order. However, okay, let's put them, let's do a couple of ratios here. I'm going to do this one right here. I'm going to group these two, and I'm going to group these two. Okay, all right, from the first factor, notice that n factorial is the largest between n factorial and n minus 1 factorial. On the second factor, notice n plus 1 factorial is the largest between n plus 1 and n factorial. So I'm going to write this in green actually, so you can see where are they coming from. Well, actually I'm going to highlight them instead. So n factorial, not n factorial, hold on, that's just going to be n times n minus 1, and I'm going to stop here. N factorial times n factorial, and the denominator, it's going to be n plus 1 times n factorial, and I'm going to highlight with green what I expanded using the factorial definition. Okay, something's going on here. Okay, yeah, all right. So I'm going to highlight this with green, and I'm going to highlight this with green to relate what was expanded. So now it's time to divide out common factors. This guy, that guy, that guy. And we are left with n divided by n plus 1. Okay. Letter H, I'm going to leave it to you. So have fun with this one. That's what this means. Have fun. Okay. All right, now let's go ahead and define power series. So power series are series in the following form. Okay, so we have a series sigma n equals 0 to infinity of some a sub n, some general rule times x to some power, in which all these coefficients are called the coefficients of the series. Okay, in a more general form, I mean, that's like first the ones that I highlighted. First of all, that's like the simplest form of a power series. But in a more general form, we are going to have series that are centered at A. We're going to talk about this centering at this point, at this other point. So you will see later as we go over the different examples. Okay, and let's define that. Let's highlight. So when you see a series that has x minus a, we say that the power series is centered at A. For example, if we have some sigma whatever x minus 5 to the n, this is centered at 5. If we have some sigma x plus 3 pi over 4, for example, like a trigonometric 1 to the nth power, it is centered at negative 3 pi over 4, as you will see more in detail when we get to the examples. So in general, a function, what do we do with power series? Power series are special ways to represent functions, like the function e to the x, like the function sine, cosine, 1 over 1 minus x, so natural log of x's. So there are ways to represent those functions in terms of series, and more in general, they are going to look, they're going to have this look, more or less. So as we go through the different examples, and when we look at the next section, by the way, we're going to look at different actually lower limits and different ace events that we're going to make a connection very interestingly between this section and the following one. All right, so let's just have fun and play with this power series. We're not going to calculate them, or rather find them from a given function f of x. We're actually given the series here. So all just to have fun and just to have some fun, they're just asking us to evaluate a few terms. So we start our lowest limit at n equals 0. So all we do is x to the 0 plus x to the first plus x to the second plus x to the third. We don't have to do too many, dot plus dot dot dot. And let's just simplify this. X to the 0 is 1, x to the first, we don't need to write that 1, that's just x, plus x squared plus x cubed plus dot dot dot. Okay, we don't have to do just a few. Watch out with this guy on letter B right here. -1 to the n power. Again, that's called an alternating factor. That's going to make our series alternate between plus and minus. Okay, so let's expand, writing every single detail. -1 to the 0, x to the 0 divided by 0 factorial plus -1 to the first, x to the first divided by 1 factorial plus -1 to the second, x to the second divided by 2 factorial plus -1 to the third, x to the third divided by 3 factorial. That's enough. Okay, so what is 0 factorial? By definition, we say 0 factorial is 1. Okay, so this one right here is 1. -1 to the 0 is +1. X to the 0 is +1. So all we're left here is with a 1. Okay, I'm not going to write the plus sign yet. I'm gonna write first the answer to raising -1 to the first power, which in this case is -1. So that's going to be a negative. X to the first power is simply x, and 1 factorial, this guy was simply 1. I don't need to write that 1 in the denominator. The third term of this series will be -1 to the second power, which is +1, x squared divided by 2 factorial, which is 2. And the next term will be negative because we have a negative raised to a naught power. That's a minus x cubed divided by 3 factorial, which is 6 plus dot dot dot. And that's final answer. I forgot the plus dot 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 here. Let's look at a more complicated series here. All right. So in this case, notice we're starting our lower limit at 2. So that's our first term. So -1 to the second times x minus 1/4 to the 2 times 2 plus 1. The whole thing divided by 2 times 2 plus 1 factorial. Plus, for this one, I'm just going to expand 3 terms. -1 to the second, x minus 1/4 to the 2 times, well, this is not to the second, to the third rather, 2 times 3 plus 1 divided by 2 times 3 plus 1 plus -1 to the 4th power, x minus 1/4, 2 times 4 plus 1. Divide that by 2 times 4 plus 1 factorial plus dot dot dot. Okay, we don't need to expand too many terms. All right, let's simplify this. So here we are going to get the following. I'm just going to write this below because I don't want to write everything. Okay, 2 times 2, this will be 4 plus 1, this will be a 5 factorial, which happens to be 120. This is 2 times 3, which is 6 plus 1. That'll be a 7 factorial, which happens to be 50, 40. And this is going to be 2 times 4, which is 8 plus 1, which is 9 factorial, which happens to be a huge number, 362,880. Okay, now this negative 1 to the second will give me a positive term. Negative 1 to the 4 will give me a positive term. As opposed to the second term, negative 1 to the odd, which is 3, it's going to give me a minus. Okay, and the exponents, I'm going to simplify them here. 2 times 2, which is 4, plus 1 is 5, 7, 9. So the series here will be, these few terms, 1 over 120, x minus 1/4 raised to the 5th power, minus 150, 40, x minus 1/4 plus 362, 880 under 1 times x minus 1/4 to the 9th power plus dot dot dot. We don't need to write any more terms. Imagine how big this denominator be for 11 factorial. If you want to have more fun, go ahead and write more terms, and the factorial symbol, you can find it on any calculator. Okay, let's do the reverse. Now we're given the sequence, well, rather the sequence of terms with plus signs, or in plus and minus signs in between. We need to write this using summation notation. Summation notation involving sigma. Okay, that's what we do. That's what summation notation means. Okay, so let's find a pattern here. Notice the powers of x are 1, 2, 3, 4. Okay, so if we start our series at n equals 1, goes all the way to infinity, we are going to have x to the nth power. However, and by the way, there's a little typo here. It shouldn't be 81. This should be 64. Okay, and in this case, we are going to find a pattern for the numbers in the denominator. This is the same as saying x to the first divided by 1. Okay, so this is, do you recognize these numbers? 1, 8, 27, 64. Yes, that is correct. This is the sequence of cubes, of perfect cubes. That is n to the 3rd power. All right. And that's all we have to do for this one. No more, no less. Okay. All right. Let's see. Let's look at letter B. And notice the alternating signs. We have a combination of pluses and minus. So that means that our series, sigma, it's going to have some sort of negative 1 to the nth power, or maybe plus 1, or maybe plus something. We don't know yet. We're gonna figure this out soon. All right. Notice here we have 1, 2, 3. So the numbers increase by 1 every single term. Okay, so how about I put an n to represent that sequence of 1, 2, 3. But notice this, 4, let me actually highlight this guy right here so you can see what is that representing. And let me highlight this, 4, 5, 6. Okay, how much bigger is the number 4 from 1? How much bigger is the number 5 from 2? How much bigger is the number 6 from 3? Do you see the difference between them? Yes, that is n plus 3. And of course, this series is centered at x plus 5, x plus 5, x plus 5. And notice the powers here. Notice the powers is a 1. These powers are coincident with the first n. So we are going to have x plus 5 to the nth power. So we are going to start our series at n equals 1 to infinity. Okay, and then let's see if it works. Notice I have to have the first term to be a negative. So if we start at 1, do we get this correct? Negative 1 to the first? Yes, it's negative 1, the first negative that we start with. Okay, let me erase this so you don't get confused about it. So this will be our final answer. Okay. All right. Now, what about the interval of convergence? What is that and how do we get it? So, okay. So suppose again we have this power series, this function that can be written as a power series. Okay. So in this case, how is this series different from the series that we covered on the previous sections? The difference, yes, that is correct. The difference is this x right here. We didn't have that x, that variable in the previous examples. Okay? Now, the thing is, if we assign a value, if x is assigned a value, then the power series, this power series become an infinite series with constant terms, like the ones that we dealt with on the previous section. Now, can we plug in just any value of x to a given function? Well, yes, we can do. However, we are going to be looking for values of x that make a series converges. So that's what we're going to do in this case. Find the set of numbers as, in this case, represented as an interval in a way that those numbers give us convergent series. Okay, and we have done a little bit of that on this previous section, but let me give you just briefly like the bigger picture of what this is about. Okay, suppose I have f of x equals sigma n equals 1 to infinity of the function, I'm gonna say x over 5 to the nth power. Okay, this is what I'm going to do here. Okay, I'm going to do the following. I'm going to do f of 1. Let's see if f of 1 is it's going to give us a convergent series. Okay, so I'm going to do this n equals 1. Notice in this case we're not looking at n, only x rather. So I'm going to, this will be 1/5. Do you recognize this series? Yes, yeah, that's correct. This is a geometric series with r equals 1/5. And because this number is less than 1, this is a convergent geometric series. Okay. Now, let's try other numbers. Let's say f evaluated at, okay, how about I copy this instead? And then I'm going to move it here. Okay, how about f evaluated at, I don't know, maybe 3. How about 3? F of 3 is the series convergence for f for x equals 3. Let's find out. Okay, so again, yes, you're correct. This is a geometric series with r equals 3/5, which is less than 1. And again, this is also a convergent series. Now, the thing is, I cannot just plug in all the numbers to exhaust to find out whether what are the numbers that are okay for this series. Let me do one more. How about, let's see, let me evaluate the series for x equals 7. What's going to happen here? So now if you look at the ratio, the common ratio of the geometric series, we have r equals to 7/5, which in this case is greater than or equal 1, which is a divergent series. Okay, so it looks like, let me do another one. Just one more and we're good to go. Let me do 5. Let me do 5. In this case, what are we going to get? Check this out. Sigma 1 to the n equals 1 to infinity. This is going to be a divergent because this is 1, which is greater than or equal 1 for a geometric series. So it looks like there is a limit, okay, for this is x equals 0. This is going to be 1, 2, 3, 4, 5. Okay, maybe I should make this smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, looks like the good endpoint is 1, 2, 3, 4, 5. And if you try the negative side, which I didn't try any negative numbers, but if you try plugging in -3, -4, again, you take the absolute value of the common ratio, okay? And, well, let me do one with negative. Why not? Okay, let me do one with negative. I'm going to do, this time, I'm going to do -4. Okay, so R, which is -4/5, if we take the absolute value, we get 4/5. And this is still less than 1, so converges. Do you see what is going to happen if you plug in a -5? It's going to diverge again because you're going to have -1 to the n power, and you are going to have an oscillating series oscillating between -1 and 1, and it's not going to go anywhere all the time. So 1, 2, 3, 4, 5 looks like -5 and +5 are the limits. But I mean, look at what I'm doing. Do we have to do all this for every single series by exhaustion? No. We don't have to do this. I'm going to call this the interval of convergence. Everywhere else, the series diverges. And we call this, even though we don't talk about it, but this is, I mean, properly speaking, giving it a name, this is the interval of, those are the intervals of divergence. And no, we don't have to do this picture all the time. This is just to show you what are we going to do by means of taking a limit in the next set of exercises, okay? So this is basically the bigger picture of it. All right, so what about that interval of convergence? Okay. So okay, again, that set of all values for which the power series converges is called the interval of convergence. Okay, that's what it's called. Now, so this interval of convergence is coincident with the domain of the given function. So for example, if we are given, you will see when we find the domain of e to the x, when we see the series representation, I'm going to put it with question marks because we don't know what that is yet. We know that the domain of an exponential function, it's the set of all real numbers, and for the natural log function, the domain is going from 1 to infinity. Okay, so we are going to, when we find the radius of convergence, this will coincide with the domain of the function that is being represented. So in other words, interval of convergence, it's a fancy way to say domain of a function. The thing is, the interval of convergence goes with the power series representation of the function, and simple domain goes with the function itself. Okay, what is the process to find out what interval of convergence is? Okay, so we are going to be given a series. Focus on the part that doesn't have an x, that is the a sub n. So yes, we are going to still have this x minus a to the n, which tells us where the series is centered at. However, we are going to take only the a sub n, the part that doesn't have any excess. Plug it in here, divide by a shifted by n plus 1. And we are going to have three different criteria. If r equals 0, that limit that we get, then the series will only converge for x equals a, the number that is centered at. Otherwise, if you get a number that lies between 0 and infinity, then the series will have an interval of convergence between a minus r and a plus r, where a is the value of a in which the series is centered at. And finally, if you get some r equals infinity, that is, the radius is infinity, in infinite radius, series converges for all x. Let's do examples to make more sense out of what we just have read and highlighted. Okay. Okay, find the interval of convergence of each of the following power series. Okay, this is what we do. Highlight the part that doesn't have the x. For now, we are going to ignore this x plus 2. But we are going to have a meaning to this x plus 2. Again, when a series is centered at x minus a, it has an x minus a to the n. This is centered at x equals a. In this case, we have x plus 2. That means center at c equals -2. That is where it's centered. We'll make more sense out of that when we find this interval of convergence. Okay, so a sub n. What is a sub n? A sub n is the quantity I highlighted with yellow, which is n cubed. I'm going to shift this a sub n to n plus 1. Wherever you see the n, replace with n plus 1. To find the radius of convergence r, big R, this will be the limit as n approaches infinity of the absolute value of a sub n divided by a sub n plus 1. Okay. Divide, okay. So let's plug in limit n cubed over n plus 1 cubed as n approaches infinity. However, in this case, we may remove the absolute value terms because in this case, it doesn't matter. They are both positive quantities. Now, how are we going to deal with this? Okay, let's make this easy, simple. I know the textbook, if you read the textbook, the textbook has a different approach. I'm going to take a different approach. So the numerator, no more absolute values. The numerator It's going to give us only n cubed. That's all we have. If we were to FOIL this, n plus 1 times n plus 1 times n plus 1, we will multiply n times n, that'll be n squared, and then eventually we multiply that by n, so we are going to have some n cubed plus garbage, plus a lot of terms. And notice in this case, we can just go with the ratio of the leading coefficients, which is 1 over 1, which is 1. That's the shortcut, if you will, to evaluate polynomial limits. Rational limits involving rational expressions. You look at the leading terms. If you have the same degree in the numerator and the denominator, then the limit will be the ratio of the leading coefficients. 1 divided by 1, this will be 1. It's easy as that. All right, so in this case, we have a number between 0 and 1. This will meet the second criteria. We are going to have A, which for us, our A is -2, and R is 1. Okay, let me write that down again. The center is 2. That is this number that we just got is the radius of convergence. And you can think of a circle, for example. Okay, so we have this center of a circle at -2, and the radius goes 1 unit. If you draw a circle, that means this series will have two endpoints, -2 plus 1 and -1. That's going to give us -3 and -1. Let's represent this as an interval. So first of all, let's represent this interval of convergence. Okay, it's going to be the center plus and minus whatever we got for the radius, that is -2 minus 1, comma, -2 plus 1, which in this case the interval is -3 to -1. So that is, we can plug in the number except the endpoints, because notice the parentheses. Notice the parentheses, we cannot take the endpoints. We can plug in -2, and that's about it. -2, -2.1, -2.2, -2.3, but never -3, or -1.9, -1.7, -1.6, or many decimals, depending on the purpose here. All right. Let's look at another example. Letter B, n factorial times x minus 1 to the n power. First of all, this series is centered at x equals +1. We changed the sign of what we have here, just the same way we did earlier here. We changed that plus into a minus to find the center. Let's highlight the general term. In this case, it's just this tiny factorial. Okay, let's see what are we going to have here. So a sub n, which is n factorial, and a sub n plus 1, it's n plus 1 factorial. Let's find that limit to find r, the radius. That's the limit n approaches infinity of a sub n, absolute value of a sub n divided by a sub n plus 1, which equals limit n goes to infinity of absolute value of n factorial divided by n plus 1 factorial. I'm going to remove these absolute value bars because we don't need them. So limit and factorial, and I'm going to expand the largest of the factorials at the same time, just the same way we did it on the exercises a few pages ago, remember? So this is going to be n plus 1 times n, one less, and factorial, because the reason why I don't continue n minus 1, n minus 2, etc. is because this is coincident with the factorial we have in the numerator. To divide it out, that n approaches to infinity. So we're going to have limit n approaches infinity, 1 over n plus 1. What happens if we plug in infinity? This goes to 0. Okay, what is the criteria for 0? Let's go up here. If the radius is 0, the series only converges for whatever the value in which this series is centered. So the series only converges to, or converges for, not to, x equals 0. Okay, how come? Let me give you a few. Let's examine this series. Sigma n factorial x minus 1 to the nth power, and starting at n equals 1 to infinity. Okay, so for x equals 1, which is the value at which the series is centered at, we are going to have sigma n equals 1 to infinity of n factorial. Notice we're plugging in for x, not for n, and this is going to be 1 minus 1 to the nth power, which will be 0 to the nth power. Zero to the n power, which will be just 0. N factorial times 0 starts at 1, not 0. And this will be the sum of all the terms 0. So 0 plus 0 plus 0, what are you going to get here? This converges to 0. This series converges to 0. But I mean, if we plug in another number, let's say 1. No, not 1. I mean, that's what the one that we just did. Let's say 2. Sigma n factorial 1 to the n. So we're going to get, sigma n factorial times 1 to the n. Look at this series. What is going to happen? Plug in 1 n factorial times 1 to the n. 2 factorial. 3 factorial. Huge, huge, huge. It's just going to blow up to infinity. Even if you do for, what about -1? We're going to have n factorial times -1 minus 1 to the nth power, n equals 1 to infinity. This will be n factorial -2 to the nth power, sigma n equals 1 to infinity. And in this case, notice what it's going to happen. It's going to bounce between positives and negatives, and at the same time, this is going to be getting bigger, smaller, big and smaller, but bigger every time. Bigger every time. Looks like it's going to do this big, small, something like this. That's what it's going to do. This one is just going to do this, going to get bigger. This one is just going to remain constant at x equals 0. I mean, y equals 0. Okay, so that's how the series only converges for, and I need to correct this real quick, not x equals 0. The radius is 0, but the series converges for x equals 1, which is the end point, the center point only. All right, let's do another similar example. This is going to be, we're going to have the n factorial in the denominator, and this is going to be a game changer right here. So let me just rewrite it so we can have some sense of isolation. By the way, this is not supposed to be a 2. This is supposed to be a 0. N equals 0, x to the n over, oh no, I'm repeating this, 1 over n factorial times x to the n. And by this term, this is telling us that the series is centered, the center is x equals 0. Okay. What is a sub n? A sub n equals 1 over n factorial. What is a sub n plus 1? Replace n with n plus 1. 1 over n plus 1 factorial. Now let's look at the radius of convergence. R equals the limit as n approaches infinity of the ratio of a sub n with a sub n plus 1. In this case, limit as n approaches infinity, 1 over n factorial, 1 over n plus 1 factorial. Absolute value bars, and these are going to start to get a bit ugly. Okay. Now notice what am I going to do here? I'm going to group this guy with that guy and this guy with that guy. So I'm going to multiply by the reciprocal of the denominator. Limit 1 over n factorial times n plus 1 factorial. As n approaches infinity, no more absolute value bars. Okay. Now, in this case, we are going to expand to simplify the largest of the factorials, that is n plus 1. Limit n approaches infinity of n plus 1 times 1 less, which will be n factorial over n factorial. And in this case, divide out these two to cancel those n factorials. N factorial, n factorial. Go away. So limit equals, limit as n approaches infinity of n plus 1. What happens if we plug in infinity? We get infinity plus 1, which is simply infinity. So we have an infinity radius of convergence. So what do we conclude here? We conclude that the series converges for all x. That is, we can plug in any number to this series and it will be guaranteed that will converge. Not like this one, remember? Let me just go back a little bit. Remember, this series right here had a little bit of trouble for certain values of x. We were okay to plug in 1, we were okay to plug in 3, but not 7, not 5, even -4. But in this case, this one will converge for all x. So letter examples A through C gives us one example of each type. Let's do more examples. I have 3 more examples to show you. Some of them are going to look a little bit crazier. And yes, that's what we're going to have on the homework and on a future exam. So I want to prepare you for those. Okay, so let's look at the next one. The next one, letter D. Okay, we would need to simplify this before we can find out what general term is in this case. Okay, so this is what we do. I'm going to have And by the way, this one series, I have a little typo here. This also starts at 0. Your notes may not have that typo. Your notes might be okay. So this series, this is the same as saying sigma n equals 0 to infinity. This negative to the n is the same as saying negative 1 to the n power, and then x to the n divided by 4 to the n. So we are going to focus only on the part that doesn't have x's. That is going to be our a sub n. Negative 1 to the nth power over 4 to the n. And it's worth mentioning that the center of this series, the center is x equals 0. What is a sub n plus 1? A sub n plus 1 equals negative 1 to the n plus 1 divided by 4 to the n plus 1. Now let's find the radius of convergence. R, which equals the ratio between, first of all, limit n approaches infinity, the ratio of negative 1 to the n divided by negative 1 to the n plus 1 divided by 4 to the n plus 1. Okay, so notice what is going to happen here. I'm going to just drop these guys right here. Negative 1 to the n, negative 1 to the n plus 1. We can just erase those in the next step. Why? Let me explain that. Because we are going to have the absolute value. Okay, we have absolute value bars. This negative 1 to the n is going to give us a bunch of positive negatives, but that absolute value symbol will eliminate any positive or negative, so we're good to just ditch these two quantities I highlighted in purple and be left only with 1 over 4 to the n divided by 1 over 4 to the n plus 1. Again, we're going to have some sort of a complex fraction. I'm going to multiply by the reciprocal of the denominator. Limit 1 over 4 to the n times 4 to the n plus 1 over 1. And I'm going to use laws of exponents to simplify this guy so I can divide out some factor of 4 to the n, as you will see. Limit of 4 to the n times 4 divided by 4 to the n as n approaches infinity. Okay. Notice how these 4 to the n's will cancel, and I'm going to be left with the limit as n approaches infinity of the number 4, and in this case this will always be 4. Okay, so in this case we got a number between 0 and infinity. So in this case we are going to have the interval of convergence as the center plus minus the radius of convergence. In other words, we're going to have 0 plus and minus 4. That is, using interval notation, goes from negative 4 to positive 4. Okay? And that's the interval of convergence. Maybe I should use the same notation here. Center plus minus 1 for the first example. Okay. All right, let's look at another example. Let's flip the page. and look for more interesting series like the ones we have here. Okay, now let's see. So number one, let's identify the a sub n. By the way, I'm missing an n right here, this one right there, the exponent of x plus 4. And also let's identify the center. Center is x equals -4. Okay, let's see what about this one. So let's identify a sub n, which is the quantity I highlighted in yellow. A sub n equals -1 to the nth power divided by n times 5 to the nth power. A sub n plus 1, change everywhere you see the n with an n plus 1. Okay. Didn't change the n plus 1. Give me a second. So n plus 1, 5 to the n. Okay, let's find that radius of convergence. R equals the limit a sub n over a sub n plus 1, absolute value of that ratio as n approaches infinity. Okay, this is going to look huge right here. This will be the limit n approaches infinity of the absolute value bar of the absolute value of n 5 to the n under -1 to the n divided by -1 to the n plus 1 over n plus 1 5 to the n plus 1. And as we mentioned before, we can just ditch these alternating factors, these factors that gives us pluses and minus, using these absolute value bars. These absolute value bars help us to cancel this out. So we are going to have the following. We're going to have the limit as n approaches infinity of 1 over n to the 5 to the n over 1 over n plus 1 to the times 5 to the n plus 1. So again, we have some sort of a complex fraction. Let's group each of the factors. Okay, each numerator and denominator, and then I'm going to multiply by the reciprocal of the denominator. We have limit n 5 to the n times 5 to the n plus 1 times, okay, let me erase this and change the order. That's n plus 1, 5 to the n plus 1 over 1. N approaches infinity. So what are we going to do here? I'm going to group this, and that's going to be limit n plus 1 over n, and this 5 to the n plus 1, I'm going to use laws of exponents again to write this as 5 to the n times 5 divided by 5 to the n. And we get the following. We get This 5 to the n cancel. And notice in this case, this 5 right here can be just written in front of the limit symbol. So I'm going to have 5 limit n approaches infinity of n plus 1 divided by n. This will be, again, we have, well, if you want to do it the old-fashioned way, this is limit n over n. This is 1 over n. And this whole term is going to go to 0. So we are going to be left with 1 times 5, which will be 5. Okay, so that's equal to the radius of convergence. So now from here, we are going to find the interval of convergence. Interval of convergence. And this will be center plus minus r, that is negative 4 plus and minus 5. In the negative case, negative 4 minus 5, comma, negative 4 plus 5. So that'll be negative 9 and negative, not negative 1 rather, that's going to be 1. So that's our interval of convergence for this series. What does that mean? It means, okay, the series is centered at, okay, so this is 0 right here. Negative 4, I'm going to say it's right here, right there. Okay, so negative 4 plus 5, we get 1, and negative 4 minus 5, we get. So this is the interval of convergence. These are all the set of values. This is the set of all values, rather, for which you plug in f of x to the series, you will obtain a convergent series. Otherwise, if you pick a number between 1 and infinity and negative 9 and negative infinity, your series will for sure diverge. Okay. Let's do one more and we move on to Taylor series. Okay, so number 1, let's identify the general term right here. So in this case, a sub n will be the factors that do not have an x. Okay, so a sub n equals n plus 3 squared under n factorial, and a sub n plus 1 equals n plus 1 factorial divided by n plus 1 plus 3 quantity squared, which will be actually n plus 4 squared, n plus 1 factorial. So the radius of convergence will be the limit of the absolute value between a sub n, of the ratio between a sub n and a sub n plus 1 as n approaches infinity. Okay, now this will be the limit of n plus 3 factorial under, no, not factorial, this actually is squared, n factorial here, and n plus 1 factorial, n plus 4 factorial. Absolute value of that whole thing, n approaches infinity. Okay, what are we gonna have? First of all, we can just get rid of the absolute value bars, because this is going to be absolute value of something positive. Okay, and then let me group this sort of complex fraction. So this is going to be the limit as n approaches infinity of n factorial divided by n plus 3 quantity squared times n plus 4 squared over n plus 1 factorial. And by the way, this isn't supposed to be a factorial here. This was supposed to be n plus 4 quantity squared. Okay. Now, well, let's deal with the factorials. Dealing with the factorials here, I'm going to have n plus 1, n factorial and n plus 1. We are going to simplify the largest of them to make it match with the n factorial. So this will be limit n factorial divided by, and then n plus 1 times n factorial. So as far as the factorials go, we may just cancel the n factorials. What are we going to have here? Here I'm going to have the following. I'm going to expand the binomials n plus 3 squared and n plus 4 squared. The expansion of those two binomials are respectively n squared plus 6n plus 9, and then n squared plus 8n plus 16 as n approaches infinity. What are we going to have here? Limit of n squared plus 8n plus 16 divided by n squared plus 6n plus 9 times n plus 1 factorial. Okay, now look at the denominator. If we continue the foiling, which I don't want to do, we're gonna get as the highest of the terms to have a cube. Okay, it's gonna be a cubed. So in the denominator, I'm gonna have n cubed plus garbage, and in the numerator, I'm gonna have n squared plus garbage. So we can just disregard the garbage terms and get this approximately limit of n squared over n cubed. This is basically limit n approaches infinity of 1 over n, which is 1 over infinity, which is 0. Because the radius is 0, the series only converges at its center, x equals 5. Okay, so no radius, just the center. It's just okay for the center. All right, now let's talk about Taylor series. And if you look at the formula, f to the fn, that is the nth derivative evaluated at the center point over n factorial x minus a to the n. We already worked with Taylor polynomials, but in this case we didn't see the Taylor polynomials as a series. We mentioned the series, but we didn't express this in terms of sigma notation, which is what we are going to do in this part of the section. Now, what about the formulas in the bottom part of the box? Well, keep in mind that we use those Taylor polynomials on section 11.1 to do approximations. Okay, so when it comes to approximations, guys, there is some margin of error about it, and that margin of error about it is it's typically called the remainder, which is denoted r subscript n of x. And in this case, well, a function it's defined as a series like the one that we have here, provided that the limit of the remainder, the part that we don't consider, that we basically ditch in the approximation, because again, we look for we when we did that section, we used 3 terms or 4 terms. We did a like a quadratic approximation, a cubic approximation, and so on and so forth. But what about the infinitely many terms that we didn't use? That is the remainder. And in this case, if the limit as we approach infinity is basically 0, then this is a good approximation. So let's work with some series. Let's go back to those. Yes, it's going to be a little bit tedious again, finding derivatives repeatedly. Okay, so finding the Taylor series for the function f of x equals x minus 1. Okay. First of all, f of x equals 1 over x minus 1. And then we evaluate at the center point. F of 2 equals 1 over 2 minus 1, which is 1 over 1, which is 1. Good. Take the derivative of this. Okay, I don't have time. I don't have a space here to rewrite it, so I don't want to make this a mess. F of x equals x minus 1 to the negative 1. The first derivative will be negative 1 times x to the x minus 1 to the negative 1 minus 1, which is negative 2. Evaluate this at f prime at 2. This will be negative 1. By the way, let me rewrite this in x minus 1 squared. This will be negative 1 over 2 minus 1 quantity squared. That is negative 2 minus 1. 1 over 1 squared. That's negative 1. Let's take the second derivative. Second derivative, negative 2 times negative 1. This will be positive 2 times x minus 1 raised to the negative 2 minus 1. That will be negative 3, which is the same as 2 divided by x minus 1 to the third power. So this will be evaluated at 2. So this will be 2 divided by 2 minus 1 cubed equals 2 divided by 1 cubed, which is simply 2. Let's do one more derivative. Of course, we don't have to go all the way to 5 derivatives or 6 derivatives or 23 derivatives. Just 3 terms is 3 derivatives is enough to obtain 4 terms, and then you'll see what we do. F triple prime, so negative 3 times 2 will be negative 6 times x minus 1 times negative 3 minus 1, negative 4, which is equal to negative 6 divided by x minus 1 quantity, x minus 1 to the fourth power, which evaluated is f double triple prime evaluated at 2, the center point. This will be 2 divided, actually not 2. I was copying the number above. Okay, my bad. Negative 6 divided by x minus 1 to the fourth power. Oh, hold on again. Not x, it doesn't have x anymore. So 2 minus 1 to the fourth power. Negative 6, 2 minus 1, that's 1 to the fourth power equals negative 6. Okay. All right, let's find a Taylor series for this formula. First of all, the claim is that a function f of x can be represented as a power series in the following form n equals 0, f and derivative evaluated at a divided by n factorial x minus a to the nth power. Okay, and what are we going to do here? I'm going to do, okay, for the 0th term, the f0, that means no derivative, that means f evaluated at a over a 0 factorial plus f prime of a over 1 factorial x minus a to the first power. That's basically the linear approximation that we did in 11.1 section, and then f double prime of a over 2 factorial x minus a to the second plus f triple prime evaluated at a over 3 factorial x minus a to the third power, and so on and so forth. The fourth derivative over 4 factorial x minus a to the fourth, the fifth derivative evaluated at a over 5 factorial times x minus a to the fifth, so on and so forth. Again, we're going to use 1, 2, 3, 4 terms only. That's enough. Okay. So we're going to plug in f of x, which is, by the way, I'm not going to write f of x symbol anymore. I'm going to write the actual function, which is 1 over x minus 1. This will be f evaluated at a. What did we get? Let me use colors to relate these numbers. F evaluated at the center is 1, which is this guy right here. F prime evaluated at the center, which is 2, is the number that is going to go here. Again, if we recall from the definition, those numbers are the coefficients of this Taylor series. And then F double prime evaluated at the center, that'll be this number that is going to go here. And last but not least, f triple prime evaluated at 2 equals -6. That's the number that goes here. Okay, this is the only example in which I will do this coloring. For the next, I will just write the numbers where they correspond. Okay, so what is f of a? F of a, the number in yellow, which is 1. Okay, that is 1 over 0 factorial, which is 1. And then in this case, x minus 2 to the 0 power plus f prime of a, the green number, -1 over 1 factorial, which is simply 1 times x minus 2, and that's to the first power, plus f double prime, which is 2, the number in blue, highlighted in blue rather, over 2 factorial. And I know what you're thinking here. Actually, let me keep everything in terms of factorials. I know that you want to, you know what, never mind, forget about the factorial thing. I'm going to do that for the next example, in fact. Okay, so 2 factorial is 2. That'll be x minus 2 to the second power plus -6 over 3 factorial, which is 6. X minus 2 to the third power plus ... Okay. All right, so x minus 1 under 1 will be 1 over 1, which is 1, and any quantity x minus 2 to the 0, like x minus 2 to the 0 power, will always be 1. And let me actually keep the x minus 2 to the 0 for a reason. And then this will be plus minus, that's minus x minus 1 to the first plus 1 times x minus 2 to the second minus 6 over 6, which is 1, x minus 2 to the third. And if continue this pattern, we are going to have plus, minus, etc., etc. Now, what are we going to do here? What are we going to do here? So in this case, we are going to write this 1 over x minus 1 in terms of a Taylor series. N equals 1 to infinity. Well, actually, n equals to 0, not equals 1. Okay, I would need you to write to see. I need you to see the pattern x minus 2 to the n. Well, that's kind of obvious because that's where the center of the series is located at. But look at this alternating plus minus plus minus. That requires one of those so-called alternating factors. Okay, and let's look at this series. And let's find the interval, the radius and the interval of convergence. So R, okay, this is, by the way, the first answer, the series representation of the function. This will be the limit as n approaches infinity of the quantity. Again, it's just a sub n over a sub n plus 1. Okay, a sub n, which is -1 to the n, and then divided by -1 to the n plus 1. Okay, again, like we did on the previous examples, these are alternating factors that become pluses and minuses, but they are not going to matter because of the absolute value bars. We can get rid of the absolute value bars and ditch these two alternating factors. And approaches infinity of 1. What's the limit of 1? 1. So the radius, this is equal to the radius of convergence. So the interval will be the center plus minus the radius. Okay, in which in this case the center is 2 plus minus the radius, which is 1. In other words, it's going to be 2 minus 1, which is 1, and 2 plus 1, which is 3. So we got one of those examples. We are given a function. You use the Taylor procedure to find the Taylor series representation of a given function. Okay, now let's look at another example. The function e to the x. Okay, let's start by evaluating f of x, which is e to the x. F evaluated at 0, that's e to the 0, which is 1. Take the derivative of f of x, that's simply e to the x. F prime evaluated at 0, it's e to the 0, which is 1. F double prime of x, it's itself e to the x. F prime double prime of x evaluated at 0, e to the 0 equals 1. Let me do one more. I know it's kind of redundant. It's the same. I don't see anything interesting, but you'll see. Triple prime, F triple. You'll see how interesting this will become on the next example. But I need you to give you a foundation first with this example first. Okay, so let's write down f of x equals sigma n equals 0 to infinity of the n derivative evaluated at a over n factorial times x minus a to the n factorial. By the way, in this case, the center is 0. Okay, so we're going to have the following. We're going to have f of 0 over 0 factorial. In this case, I'm going to leave the factorials. F of 1, f prime, not f of 1, f prime of 0. Okay, let me make this look better. Plus f double prime evaluated at 0 over 2 factorial plus f triple prime evaluated at 0 over 3 factorial, and that's enough. We don't have to write 25 terms or 57 or 117. We don't have to do that. Just the first 3 or 4 will give us a big clue about how to write the function f of x in terms of power series. In this case, in particular, the function f of x e to the x. So what is f of 0? Let me highlight this again like I did on the previous example. In this case, notice they are all ones. They're all ones. Oops, I forgot to highlight one. I'll go back to green. Okay. So we are going to find, oh no, I forgot something. Okay, let me erase all of it here. I forgot the powers of x. Okay, so we have x to the 0 plus f prime of 0 over 1 factorial, x to the first plus f double prime of 0 over 2 factorial times x squared plus f to the f triple prime of 0 divided by 3 factorial x cubed plus dot dot dot. Okay, and highlight, okay. So now, what do we do? Okay, so this is 1 over 0 factorial. E to the x is 1 over 0 factorial x to the 0 plus 1 over 1 factorial x to the first plus 1 over 2 factorial x to the second plus 1 over 3 factorial x to the third power plus dot dot dot. Do you see the pattern here? E to the x equals 1 sigma n equals 0 to infinity. Okay, notice this 1 in the numerator is always there. The powers of x go with the denominator, with the factorial number. Do you see 1 factorial, 1 power, 2 factorial, 2 power, 3 factorial, cubed power, and this will be divided by n factorial. So e to the x is the function, the exponential function e to the x centered at 0 will have this series representation. Now let's find out what interval of convergence is. But wait a minute, didn't we do this as one of the exercises? Let's go up here. And it turns out that we have it here. It's precisely this one right there. And for this one, what did we get? Remember, we got that the series converges for all x. What does that have anything to do with the domain of the function? Okay, let me go back to the series. So we already got from earlier that the series converges for all x. What does that mean? Well, so yes, we can plug in any number to x and we are going to have a convergent series. Now we have f of x equals e to the x. Now let's connect everything that we did in this section. So back when we were defining the Taylor series, or rather the power series, we mentioned that the interval of convergence is coincident with the domain of the function. What is the domain of the function e to the x? Isn't it all real numbers, rather negative infinity to positive infinity. Isn't that the same as saying the series converges for all x? All real numbers. So that's where we connect the idea of power series representation with the corresponding function. Domain, interval of convergence, same thing, just written in a different way, mentioned in a different way, but it's ultimately the same thing. Let's do another example to wrap up this section. Okay, it's going to be looking very similarly to what we got earlier. So, okay, f of x equals e to the 4x. F evaluated at 0, it's going to be e to the 4 times 0, which is simply 1. F prime, be careful here, things are going to change here. This is 4, and this is 4 e to the 4x, which is, evaluate this at 0, 4 e to the 4 times 0 equals, this is 1 times 4, this will be 4. The second derivative, that's 16 e to the 4x. Evaluate this at 0 equals 16 times e to the 4 times 0, which is 16. Triple prime, just that's how far we get. 16 times 4 isn't that a 64? E to the 4x. (64) and that's 64 times 1, which is 64. Okay, now let's write this as a power series. F of x equals sigma n equals 0 to infinity of f nth prime evaluated at the center over n factorial times x minus a to the nth power, where a is the center of the function. So what are we going to do here? So I'm going to write this as f of x equals f evaluated at 0 over 0 factorial plus f prime evaluated at 0 over 1 factorial times x to the 0. I almost forgot the powers again. X to the first plus f double prime at 0 divided by 2 factorial x squared plus f triple prime at 0 divided by 3 factorial x cubed plus dot dot dot. What are these coefficients? So in this case, f of 0 is this f of 0, which we got to be 1. F prime of 0, which is this f prime of 0, which we got to be a 4. F double prime of 0, which is this one that we computed earlier, and we got it to be 16. And last but not least, f triple prime at 0, which is the one that we got here, which we got it as a 64. Okay, let's plug this in. So here we are going to say that e to the 4x equals what is that? 1 over 0 factorial. I know you want to simplify these factorials, but I wouldn't do it if I were you. X to the 0 plus 4 over 1 factorial x to the first power plus 16 over 2 factorial times x to the second plus 64 divided by 3 factorial times x to the third power. Okay, so now our job here is to do the following. Find, by using a pattern recognition, a series representation for e to the 4x. Well, let's start with sigma n equals 0 to infinity. Well, that's something to start with. That's something. Okay, let's look at the sequence of terms in each denominator. We have factorials, very similar to what we had earlier, and factorial in the denominator. And now let's look at the powers here. The powers of, the numbers, the numerical coefficients. I mean this 1, 4, 16, 64. Hopefully you recognize this pattern. May not be really obvious, but look, what did we do here? 1 was multiplied by 4 and then times 4 and then times 4. Doesn't that look like powers of 4? 4 to the 0 power is 1, 4 to the first power is 1, 4 to the second power is 16, and 4 to the third power is 64. So what are we going to have here? 4 to the n power x to the n power, and this is the series representation for e to the 4x. I know, yes, I know what you're thinking. Are we going to do this every single time for every single section? Well, for the homework, you will be assigned a couple of those to do the long method. However, in the next section, I'm going to show you a way easier way to write functions into the series representation in seconds, literally seconds, not 10-15 minutes like we did here. For example, what if I ask you to write the series representation for f of x equals x cubed times e to the x squared? Yes, we're going to do that. But do I want you to do it during this long method? Okay, well, okay, center at c equals 5, for example. Okay, f of x, it's that now. F of 5 equals 5 cubed e to the 5 squared, which will be 125 e to the 25. What if I ask you to do the first derivative? You don't want to do this. Yes, it's a product rule, it's not going to take too long, but then the second derivative, multiple product rules. Then the third derivative, multiple product rules. You don't want to do that. I'm going to show you a way to write ugly, like really ugly looking functions. Write them in sigma notation in seconds. I'll show you how to do that on the next section. See you then.